Welcome back, everyone. We've got an incredibly exciting explainer lineup for you today. You know, over the last couple of years, we've all watched AI totally master language and vision. It's essentially conquered the digital realm. But getting that same AI to actually move and act in the physical world, oh man, that is a whole different ballgame. So today, we're going to walk step by step through this rapid evolution of embodied VLAs. This is the breakthrough tech that's literally allowing AI to step off our screens and right into our physical reality.
Okay, let's just dive right into the roadmap. First, we'll look at the robot chores problem. Then, RT2 in treating actions as words. Next up, the need for speed, followed by GR02's two minds for humanoids. And we'll wrap up with data, co-training, and safety.
All right, starting with Section 1, the robot chores problem, high dimensions and high stakes.
To really appreciate this breakthrough, we've got to understand the sheer mind-bending complexity of physical movement. It's a problem that has actively stumped roboticists since the 1970s. I mean, think about this paradox. We live in a world where an AI can instantly write an award-winning poem or spin up photorealistic images out of thin air or even pass the bar exam, right? But if you ask that exact same superintelligence to simply fold your laundry or, clear a dinner table, it completely fails. So why on earth is it so incredibly hard to build a robot butler?
Well, the answer lies in a few massive challenges. You see, physical space operates in continuous, high-dimensional action spaces. Just picture a standard robotic arm. You got 7 joints plus a 3-joint gripper. That requires calculations across 10 different dimensions. And it doesn't just do the math once. To move smoothly, it needs to hit a strict 30 Hz control loop. That means the AI has a ridiculously tight 33 millisecond budget to calculate and execute every single action. Now combine that with the fact that robot training data is insanely scarce, especially when you compare it to the billions of text documents on the web. And add in the extreme safety risks of a heavy metal arm swinging the wrong way. Yeah, you can start to see why the physical world is basically the ultimate boss fight for AI.
Moving right into Section 2, RT2, and treating actions as words. So, the real inciting incident of this whole story happens back in July 2023. That's when Google DeepMind introduced RT2, which brilliantly shifted how robots understand physical movement entirely. This introduced the world to the VLA, or Vision Language Action Model. And guys, this is the crucial missing link. Your standard vision language models take in an image and an instruction, and they spit out text. A VLA uses that exact same architecture, but instead of outputting text, it outputs physical actions. Things like joint torques or discrete commands. Having a single model that sees, reads, and acts is the ultimate bridge between AI systems that just understand things and autonomous systems that actually do things out in the real world. To pull this off, RT2 uses a really clever trick called action tokenization. The model takes in language, like, say, pick up the red cube, it processes the vision from its cameras, and then outputs an action sequence. But wait, how exactly does a language model output physical torque? Well, it essentially treats physical movement just like vocabulary words. It literally slices a continuous range of movement into 256 discrete bins. So a 10-degree of freedom movement just becomes 10 text tokens that the robot then decodes into physical movement. It's an absolutely genius workaround.
And this single breakthrough, it kicks off a blistering timeline of evolution. We go from RT2 in July 2023 to the open source community stepping in with OpenVLA a year later. Then, Physical Intelligence launched Pi0 in late 2024, and NVIDIA dropped Groot N1 in March 2025. It's just wild how fast this is moving. And it brilliantly illustrates the iterative nature of the field because each new model directly fixed the fatal flaw of the one right before it.
Which brings us to Section 3, the need for speed. Let's move into the next phase. This is where the tech goes open source, but almost immediately hits a totally frustrating physical bottleneck. They just weren't fast enough. In June 2024, researchers released OpenVLA. It was a massive deal, an open-weight 7 billion parameter reference model built on a llama backbone. But there was a catch. It maxed out at about 4.5 Hz. It was processing physical actions at roughly 4 to 5 frames per second. Now that's perfectly fine for very slow, deliberate manipulation, but it is way too sluggish for real-time control, let alone doing things like catching a tossed object or recovering if it gets bumped. The autoregressive decoding of those discrete tokens, which essentially forces the AI to calculate every single micro-movement one by one, kind of like guessing words in a sentence, it was just too computationally heavy. Researchers quickly realized that those discrete bins from RT2 were actually incredibly inefficient. Why? Because most physical actions cluster in a tiny region of that bin space. You simply don't need 256 bins for every micro-movement. So they introduced the FAST tokenizer. FAST uses frequency domains, specifically discrete cosine transforms. If that sounds complicated, just think of it like how an MP3 compresses audio. It captures the overall shape of the movement without needing to save every tiny data point. So a 30-step trajectory that used to take 300 cumbersome tokens, now it only takes about 10 fast tokens. This single tweak sped up inference 3 to 5 times without losing any physical quality. Talk about a massive upgrade.
But honestly, even fast wasn't quite enough. In late 2024, a company called Physical Intelligence released their Pi Zero series, and they did something brilliant. They replaced discrete action tokens entirely. Instead of chopping movement up into bins, which, by the way, inherently destroys smooth continuous motion, they added a continuous flow matching action expert. It basically acts like an image generator, but instead of denoising pixels to form a picture, it denoises an entire 50-step sequence to form perfectly smooth physical action.
And I've got to say, the results were staggering. By emitting that full action sequence in just about 5 denoising steps, Pi Zero achieved an effective 50 Hz control rate. It completely shattered the speed limit of its predecessors. We literally went from a clunky, robotic 4.5 Hz to fluid, natural, almost human-like motion at 50 Hz, all thanks to flow matching.
All right, Section 4, GR002, Two Minds for Humanoids.
This brings us to the climax of our timeline, March 2025, with NVIDIA's GR-GOT and 1. Here, the architecture was basically forced to evolve again because the physical challenge scaled up so dramatically. We are no longer just controlling a single robotic arm bolted to a table. We're talking about controlling full-body, bipedal humanoid robots with over 30 degrees of freedom. To manage all that complexity, GR-GOT ingeniously maps to Daniel Kahneman's concept of fast and slow thinking. They literally split the robot's brain into 2 parts. System 2 is the planner, a massive vision language model that slowly reads the scene and figures out high-level goals at about 1 Hz. Then System 1 is the actor, a tiny, lightning-fast transformer acting as the physical reflexes, pumping out low-level joint commands at 50 to 100 Hz. This dual-system setup guarantees that the slow, deep thinking required to plan a complex task never ever blocks the rapid physical reflexes needed to keep the robot from, well, falling flat on its face.
And finally, Section 5, Data, Co-training, and Safety. Now, as cool as that is, architecture is really only half the battle. Let's look at how these models actually learn these physical skills in the first place, and more importantly, how we ensure they do it safely. The absolute bedrock of all of this, from OpenVLA right through to Pi Zero, is the Open X-Embodiment dataset. Remember earlier when we said robot data is scarce? Well, researchers basically banded together to assemble this massive, unified corpus. It features 1 million trajectories curated across 22 different robots. This is the universal training ground. Without this shared dataset standardizing the action spaces and camera views, none of this rapid open-source progress would have been remotely possible.
But there's a huge pitfall here. If you only train an AI on robot data, it suffers from something called catastrophic forgetting. Basically, it learns how to move but forgets what the world actually is. To prevent this, models use what's called co-fine tuning. They carefully mix web data with robot data. Usually it's a balanced ratio, like roughly 1-to-1 or half-to-1 web to robot data. And because of this mix, the AI can physically learn to pick up a red cube from the robot data without forgetting the overarching concept of the color red that it originally learned from reading the web. This is exactly how the model can understand a novel command like move towards the fast-moving object, even if it has never actually seen a fast-moving object in its robotic training data. It's so smart.
And lastly, if you are understandably a little worried about a 50 Hz, 200-pound humanoid robot running amok in your kitchen based on a hallucinated prompt, rest assured. Every production VLA operates under strict, hard-coded control layer checks that sit completely outside the AI's neural network. We're talking hard joint limits so it literally can't break its own arms, velocity limits to prevent any erratic swinging, and workspace bounds so the hands cannot leave safe operating zones. The absolutely crucial takeaway here is that the AI's output is always treated as a suggestion by the robot's hardware, never a direct, unchecked command.
And that brings us to the end of our roadmap. I mean, just think about it. We have gone from a clunky 4 Hz robotic arm that was tokenizing joints like text to fluid, dual-system humanoids operating at up to 100 Hz in less than 2 years. Vision language action models are the definitive bridge to true autonomous systems. So as we close out this explainer, I want you to ask yourself, as this tech makes that final leap off of our screens and steps right into our physical world, what physical tasks will you trust your AI to handle in your living room first?
It's a fascinating future, and it is arriving much, much faster than anyone anticipated. Thanks for exploring this with me today, and I'll catch you on the next one.